index. Secondary index is index for the non-ordered. Okay, non-ordered, the column as a key, index key, that is a secondary index. Most of the index used in the DBMS, the commercial DBMS, is a secondary index. Primary index is very rare. It's a very special case. And also, if we are using the key, but that is not unique, like the department ID, department number for the employee, it's a 111222 like that. So if you are using such a attribute, it's called a cluster index. So that's what we learned. Then, how can we access the data using index? First, find the index key item. For example, the link. How can we find the link? Using binary search. The reason is the index is ordered by key, always. Okay? If index is not ordered, no reason to use index. Because this index is ordered by such a key. We can always use binary search. So using binary search, so we can find the index key entry. Then using this pointer, we can access this data block. For example, if it takes the 5 block, index block, okay, how many IOs are needed to find the data? 5 block plus 1. This is for binary search. This one is for accessing the data file. Always, when we are using index to access the data file, it's a +1. So this one is the complexity, IO, number of IO to find the index key. Think about the textbook. First, you need to find the keyword, and then once you know the page number, so using the page number, we can find the contents. Okay, it's a +1, always +1. So keep in mind this. So let's take a look at this example. How much index is faster? Okay, so it's not, there's a lot of information, but you can easily understand. It's similar as the data file we have used. So employee has this information, and the record size R is 150. I'm not sure whether this is a fixed or average, but we can use a given information. Okay? This, in real DBMS, where is this information? Where can you find this kind of information? Catalog database. So catalog database is a metadata source, so you can find all this information from the catalog. So let's say this one is employed. So we have the employee. This one is employee. Okay. Then the name and SSN, address, and so on. And record size R is 150 bytes. You don't have to worry about whether it's fixed or variable here. Okay, it's a given. And the block size is the 512 bytes. And then the record size R is 3000. Then the blocking factor, we can calculate the blocking factor, right? So blocking factor is let's assume the unspanned. It's much easier. Okay, what if span? Even span, we need to use average. Okay, statistical information. In total, you should know how many blocks are used, and then you can calculate, divide by a number of record, divide by total number of blocks, then you can calculate the average, the blocking factor. But here, this is, let's assume that this is unspanned. So how many? So blocking factor is divided by the R is the flooring, then the 512 divided by 150, and this is the 3. because it's a float. So 3, the blocking factor. Then how many blocks we need? So total 3K divided by blocking factor, so 10K. So 10,000 blocks are needed. Okay, then this one is the same as using data file. So we can, if this one is ordered file, we can use the binary search, or otherwise we need to use the binary search. So you can calculate how many blocks are needed. But here we have an index. So social security number is an index. So we have index for the social security number plus the pointer. This is an index key entry, so this one point like this. This is an index file. Then, just like the data file, we need to calculate. So first, block size, index block is mostly same as the data file. So 512 bytes. Then, instead of the record size, we need to calculate this size, social security number plus the pointer size. So here, if you read the given information, SSN is the 9 byte plus, then pointer size PR is 7. So what is the size of the index key entry? 9 plus 7, so 16 byte. So this is the 16 byte. So you can see the social security number is a 9 byte. Social security number actually the 10 byte, right? Or 9 byte. Social security number is a 9 byte. So then the pointer size is a 7 byte. Do not ask me why it's a 7. It's a given information. So if we are using integer, probably 4 byte. But this one may use a different data structure for the address. Okay, then let's say index entry size here there is a RI index is a 16 byte. Then we need to calculate the same thing. Blocking factor for the index. Blocking factor is the same idea. 512 bytes divided by the 16, then it's the floor. How much is that? It's exactly 32? Let me make sure. Divide by the 16. Yes, 30. It's exactly 32. So which means how many index key entry in one block? 32 index the key entry. Okay, 32 key, 32 social security number in one block. Okay, then how many index block do we need? So number with index block, how many? It's the same thing. Total check whether this is the dense index or non-dense index. There's no mention about is the ordered file. Okay? So we assume this is a secondary index. Secondary index means it's non-ordered. So this one will be dense index. So dense index means all index key items should be here. So how many? 30,000. Divided by blocking factor 32. So then, even though it's a 0.1, 0.001, it should be one entire block. So it's a silly. So what's the value? 30K. 30,000 divided by so 32. So 937.5. So total 938. So we need 938 index block. Okay. Data block, we calculate how many block? 10K. Okay. This is the index and this is the data file. Then finally, we can use let's say the brute force way. So using only data file. If you are using the only data file, how many blocks? without using index, how many blocks do you need to search the specific data? 10, how many blocks? 10K divided by 2. So 5K. 5,000 blocks you need. Brute force. So without using this. Okay? So 5,000. Get it? On average. So then, if we are using the index, so index, because these are sorted, okay? These are sorted, we can use binary search. Search for index. So if you are using the binary search, what is the complexity of the searching index key entry? Log to based on this one. Is it floor or ceiling? It should be ceiling because it's number of block. It should be whole block, whole number. So how much is that? Probably 9 point something. It's 10 to the power of 10 is the 1K. So it's slightly less than that. So 9 point something. So this one 10. Which means when you search the one data record, so it's employed, how many blocks do you need? So how many blocks total to search? Not 10 plus, so if you search the index key item here, with the data block, total 11. Okay, so this is 11. This one is the block. Block is 30K. Right? This one should be 30K. Right? Block. Oh, the 10K. I think that this one is wrong. Okay? It's a 10K is correct. This one is the 5K. And so it's a brute force. And using index, so 10 plus 1, 11. Okay? Yeah. So this is the correct answer. Which one is faster? Using index is definitely faster. Okay? On average, without using index is a 5K. Without using index, without the 5K with index is 11. So that is the reason we are using index to speed up to search the data. Okay? Then, this is the general case of the index. What if the primary index? The primary index is data file is sorted by the social, in this case, the what? It doesn't mention the specific, it's a social security number. Social security number. So for index, we don't have to keep all the index key item, instead, one per block. One per block. One per block. Right? So how many index key entry we need? Number of blocks. It's a much smaller. Because it's already ordered. We don't have to order all the data item. Instead, only one for each the data block. So that is I'm going to quickly go over. So blocking factor is this is different from this. The block size is the 1K this time. The block size is 1K. So 1024. And the number of record is the 30K. And the record length is the R is the 100. And then the key value, the index key value is the 9 byte. And the blocking pointer is the 6. The pointer. 6. So this one will be the 15. Like this. Then what is the blocking factor? Blocking factor is the 30K. No, the block size. The 1024 divided by the record how many? It's a 10. So 10 is the blocking factor. And how many blocks we need? The blocks. So 30K, the record divided by 10 is a 3K. So 3K, 3,000 blocks we need. So if we, because this file is already ordered, we can use the binary search here, right? In case of the file is ordered file, we can use the binary search without using index. So what is the complexity of such a binary search without using index? So binary search itself is a log 2 based on 2. How many blocks? It has the 30,000 blocks. So what is the value of this? So 12 point something, 11 point something, or 12 point something. So 2 to the power of 10 is 1K, 11 is 2K, and 12 is 4K. So 11 something. So it should be the ceiling, right? Because it should be entire block. So 12 block. So without using index, for the primary index, this is for the primer and the primer. So without using order the file, data file. So it takes the 12 blocks. Then using index, so we can create the sparse index for the one item for the data block. Okay, so to calculate that, what is the index key entry? It's a 15 byte. We already got the 15 byte. Blocking factor for this one, how many? The index key entry do we need? That is the same as the blocks. Okay. So we have the one entry, another entry 4. So total how many? So 30K index key entry, not 30K, 3K. 3,000 index key entry. Okay. Then, how many blocking factor is the 1,000? 24 divided by 15. So what is the value? Let me make sure. Sometimes it's wrong. And 1,024 divided by 15. So 68.26. So is this ceiling or floor? It should be floor. Why? Because we are going to count the entire record in a block. So if this one will not be counted. So it's the floor, so 68, which means 68 index key item in all block, one block. Okay? So that's the 68 entry per block. So that is the blocking factor. Then how many index block do we need? How many index block? So we can calculate very easily. So that is this one, the block. So total 3,000, 3,000 divided by 68, and 3,000 divided by 68. It should be the ceiling. So 3,000 divided by 68. Divided by 68 is a 44.11. Like that. So this is this 45. So 45 the blocks went in. Okay, then so this one is total 45 block, and this one is the 3K block. So for the binary search of using the without using index is this one. What if using index? Index. So we can do the binary search for the index is a 48. Then this is the, how much is that? 6, 2 to the power of 6 is 64. So it's a 5 point something. Right? 32, yes. So that is a 6. So which means on average, to search the specific index key item, it takes us 6 blocks. So total, the blocks, index search, 6 plus we are going to access the data file. So 6 plus 1, so 7. Okay, which one is faster? 7 and 12. 7 is faster, it's less I/O, which means even though data file is an ordered file, so we can use a binary search, but still indexing is faster. Okay, if you not always you need to calculate. So this is a common mistake later. So a lot of database developer, database programming, the developer, they believe indexing is always faster. In general, it's fast, but not always. When?
Writing the data.
So first, there are overhead, right, to manage this one. Another issue is let's think about the extreme case, like for example, the gender, the sex is the male or female. So can we create the index for the male or female? It's a binary value. Yes, we can do that, right? But if we create the index for the male or female, so male, 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 female, 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 roughly half and half, okay? So if you are using index, you need to search here, then go to here. You need to search. How long it takes? It takes a long time because it's a binary value, 2 values only. So even though you are using index, brute force way is faster. So this is the rule of thumb. If data value cardinality is 20%. So cardinality means, think about the histogram. So like the DM, number 1, so 10%. Number 2, 10%. Number 3 is 10%. Number 4 department, 10%. So like the 12 was like around that. Then this is called cardinality. Cardinality is 10%, 12%, 11%, 10% like that. But if you draw the histogram, male or female, cardinality is 49 and 51%. It's a cardinality, very high cardinality. This is a low cardinality. At that time, if the cardinality is bigger than 20%, like this one, index doesn't work. It's even slower. Which means, what is the best case of using index? Unique data. Unique data is one by one, only one data, one data, one data. So in case of unique, case, so brute force takes a longer time, but index is better. So not always index is faster, but you need to think about such a cardinality, the distribution of the data. So if data is distributed, like the unique is the best one. In case of that is a reason, think about the not only just because the database design, but also performance. The key, primary key is important to manage the relational database. Why? Because primary key provides unique. So that means when we are using index, is so we can get the full benefit of using index. This is common mistake. So when I worked as a database administrator, so not most of the time, all the time, developer, they want to create a new index. Whenever the SQL is slow, why don't you create the index for this column? Why don't you create the index for this column? However, if you create such an index in one table, how many? One, another index, another index, another index. First, overhead and space. It takes a longer time to write the data, to insert the data. Second, it doesn't work very well. So sometimes, depending on the data, so you need the index, sometimes not. Who decide? The developer should decide. However, nowadays, the query optimizer, the calculate which one is faster, using index or without using index. Query process, query optimizer will decide. So we will see a couple of weeks later regarding to the how such a query optimizer is working. At that time, we will use the same, the performance evaluation and so on. So we have such a lot of the evaluation, like this one is for the clustering index, and this one is for the multi-level index. I'm not going to cover each and every evaluation, but at least you should understand this and the given. Okay? So then it will be useful for later when you manage the data in your programming. So whether I'm going to use something ordered file, whether dictionary, sometimes the programming data structure like the Python provide the array as a list. Actually, there's no array in Python, it's a list, or the tuple, or the dictionary, which one is faster, how the dictionary is search the keyword, and so on. If you understand the behind of the programming, it will be better for you to understand the performance of your programming application. Okay, so I'm not going to explain each and every case, but please, at least you should understand this. Definitely, I'm going to use this one for the final exam. Okay? Not exactly same. I'm going to slightly change, but if you can solve this problem, you mostly solve the problem. Okay, so what if this one is bigger, which means data size is bigger, and so like the 3 million blocks we need. You need 3 million item, index key item. So this one will be the higher number of block, right? Because it's a logarithm, it's like the monotonic increase. It's better than linear, but still, the more data you have, the longer time it takes. So even it takes a time to search index key item. Solution? So we can create the index for this. Index of index. What if the data 3 billion will be grow, and this one will be grow. So we can have another index level. So this one is called multi-level index. So multi-level index is to solve the problem of the increasing such a data. It looks like if we draw such a multi-level index in very high level, what is the name of this data structure? This one? It's a binary tree. So it's a tree structure. Tree structure has node and edges. And there are 3 different types of node. This one is root, and this one is a terminal or a leaf node. Root does not have the ancestor. This one does not have any child node. And this one is internal node. The internal node mostly have the parent and child. In case you have the 2 children, this one is called binary search. Binary search tree has the left hand, right hand side, the pointer. Okay? However, this one, how many index key entry? A number of index key entry in the block. So we are not going to use a binary search tree. Instead, general. Let's say the general tree structure, like that. So if we grow the bigger and bigger, higher and higher multi-level index, it will be eventually it's a general search tree. So we can use a search tree as an index. Okay. How can we use the search tree? How can you search the data using tree? You can always start from root. Okay? Root and then check. So for example, in this case, so I'd like to search the K. How can you search K? Because A, this node represents A. So K is bigger than the A. So go to here. So D is, the K is bigger than D. So last one, so K is, we can find the K is the pointer here. Then this one overall, this is what? Index. So this K has what? Data pointer. So you can access the K to the data. So K, this one has the pointer. So you can access the data using search tree. So if we specify each node represents what? Block. One block. Okay, so think about, so suppose that I assign the homework to program the search tree. How can you do the programming? How can you start? First, you need to define what? Node, each node structure. So for example, if you're using Java, so you can create a class, node. Okay? So this class has what? Two main things, data and method. Method will be the insert data, what? Remove the data, create the children like that. And data will be what? This is a high level diagram to define the data variable of class node. So this circle means pointer. This one. So in case of the multi-level, pointer of the next children block. This is a pointer, like the pointer to this. This one is a pointer for this. Then this one is index key. 1, 2, K, and -1, like that. So for example, so if we index like the, so 10, 20, 30, 40, 50. Then less than 10 is the first child. Child has the same data structure like that. So 5, 6, 7. And this one, so between bigger than 10, less than 20 will be created like 11, 13, 15, like this. And what about this one? It's the less than 11. Go to here, like the 10.5, 10.6. Because less than 10 should go to here. It's bigger than 10 and less than 11. This is a pointer. So this is like the how you can implement. So first you can design such a variable and any method like the creating child and deleting child, insert the data and delete, remove the data method you can create. Then after you define this, next one is very simple. If there is no data, nothing. If there is inserted data, instantiate. Using new, you can create a new node, right? And insert the data. And if this one is full, then you can create the one. The next, the children, like that. It's a kind of extension of binary search tree. So this is called the search tree. So next, this one is the pointer key, and pointer key. Question: if you have the maximum 10 children node in this search tree, how many index key items in one block? So we have 10, how many? 10 children node. And how many index key items? 9. Why? It's a -1. So think about this. How many children? 3 children. 3 children. And how many index key items? 2. Okay. Then one more thing. You need to keep in mind this index key item has not just key, also pointer, data pointer. Okay. Then we can find the data. Even though it's mentioned that very simply, it's a key but this key has the key plus data pointer. Then finally we can access the data. Okay. So let's take a look. This one is a high-level illustration of the search tree. So search tree is the straightforward, the data structure, and also used a lot in our many applications, not only database, in many others. So don't be confused. The key is less than number of pointer, children node. Okay. So this is a search tree. Order. So we are going to call the number of the children node as the order. Okay. So for example, if you allow the 3 children, 1, 2, 3. 3 children, so order P is equal to 3. Okay. So order means it's a degree. Degree means how many children you have. Binary search tree, what is the order? 2. Binary search tree 2. But we are not using binary search tree. It's the general case, it's the order P. So then, in case of order P, how many children are, how many key? 2. N minus 1, 3 minus 1. So we have 1, 2. 5 is not actually just 5. It's a simplified version. 5 plus pointer. Pointer of what? Data 5. Then we can find the data. This is an index, as I keep saying, this is an index. So, for example, here, this is a given search tree. When you search data number 3 data, how many the blocks do you need to access? How many blocks do you need? Number 3. 2. Any other? 3. So why 3? First, this one. 1 IO. Then go to 3 is less than 5. Go to here 2.
And the data.
Then data. Always we are going to add the plus 1 data. So 3 actually has the data pointer 2 here. So 3 plus 1. What about 12? 1, 2, 3, plus 1, 4. Okay? And what about the 1? 1, 2, 3, plus 1. Okay? So you can calculate how long it takes. So search tree is straightforward, easy to understand, and also easy to implement. What if there's a new data, like the 4? How can you create the 4? Which block? 4 is less than 5 goes to here. So 4 is bigger than 3. But we have space so we can insert data. Some of this, not binary. Binary always create a children node. But the 2, sometimes you can create the children node. It's not critical here. But later, B balanced tree will be critical. So you can search the node, then insert. In case of 4, you can actually do something. We will discuss what is something later. That is a search tree. Okay. But problem, we are not using search tree in a database. So that's the reason I don't explain the details of this one. So simple, but we are not using. Any idea? Why the DBMS, commercial DBMS, does not use such a tree?
Creation is something.
Creation? This is simple. Actually, you guys, I can assign the homework, and you can do 1 or 2 days. It's a simple implementation. I already gave the idea. If you are using the object-oriented program, you can use such an object by defining class as a node. Then the edge will be pointer. So pointer will be included as the data structure of the data. You can then the part you can actually put such the creation and the searching and so on. It's not very difficult.
Complex tree structure.
Complexity? Too much complex?
Many.
Usually tree is good for searching, right? What if? So do you remember? this a binary tree or not? It's a binary. What about this one? It's a still binary tree. So as long as how many children? 2 children. That's okay. What about this? Is it binary or not? It should be binary. It's a common question from the data structure. What about this? Still binary. So this is also binary, which is the same as what? Linked list. Right? Linked list. So you cannot get the full benefit of the binary tree in case of this is a common question from the data structure, right? So what about this one? This is a search tree. It can be tree we expect. Assume this is the log n. In case of binary 2, in general like this, right? This is what we expect from the tree structure. However, if the tree is like that, it may be possible if somebody insert 13, 14, 15, 16, 17, 18, such an increasing order, it will be skewed there, right? Then, how long it takes? 1, 2, 3, 4, 5. It's the same as what? Brute force. It's the same as the brute force, right? So we cannot get the benefit of such a, even we cannot use a binary. We don't know this one. So it's always a brute force. So search tree sometimes cannot be used further. We cannot get the full benefit of the tree structure from the search in case it's skewed. Then how can we address? How can we solve that problem?
The key value which is there in between those.
We can make it non-skewed data. Okay. In other words, it's a balance. Balance means balance tree. Do you remember what is a balance tree? All leaf node has the same level or only less. So for example, this one will be allowed. One less the children, but this one will not be allowed. So that is a balanced tree. If you check the data structure class, it's a balanced means is the all terminal node is the same or -1. That is the balanced tree. So if you have the all balanced like this one, it's fully balanced, but still this one is a balance, and this one is a balance. This one is a balance. This one is a balance. However, this one is not balanced because it's n-2. So this is a balanced tree. Our goal is to make this search tree as a balance. Then I can understand how long it takes. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. At least 3 or 4. Okay. However, if you do not restrict the balance or allow the skew, sometimes 1, sometimes n level. So this is not a good when you process the query. So think about which one is better. So when you travel to, so you have an interview tomorrow in the Manhattan, so Goldman Sachs, whatever. So it's 8 a.m. in the morning. So which the transportation are you going to take? Train. Why? It's a guaranteed time, mostly. But if you are driving sometimes less than an hour. If we drive to 100 miles per hour, so at midnight, takes 30-40 minutes. But in the I-95, in the morning, like the 6 a.m., it's a stop. It takes 3-4 hours. Right? On average, it's faster, but we cannot guarantee. But the train is always 70 to 80 minutes. 99% is guaranteed. So which one will be? So definitely, the train will be used. Same thing for the query processing. Query optimizer, DBMS. Think about I'd like to use this query for Sometimes it takes the 1 second, sometimes the 1 hour. This one is always the 2 minutes. Which one are you going to take? This one or this one? Even it takes 10 minutes, this one will be take. Okay? We cannot guarantee. Sometimes 1 hour, your customer will not use your database search. So this is the reason we don't want to use such a general search tree, but based on that, we are going to create a balanced tree. So balanced tree means it's called the B-tree index. So when we are saying the B-tree, it's not binary. Binary cannot be used, right? It's only the 2 children. Binary cannot be used. Instead, we are using balanced the tree structure. The next question, how can you make it balanced? This one is actually the balance is coincidence. Okay? But how can you make the balance? Any idea?
Considering all the keys and then taking
You consider what?
all the keys, if it is a linked list kind of a thing.
Linked list. That might be, but so practically, if I ask you, so why don't you make the balanced tree? How can you make the algorithm? Who are the very high level your strategy? How can
Take a key value, which
Key
is
value.
in the center.
center? That's also a good idea. Any other? Take a look at the search tree. How can you create the new node or how can you insert the data? You are going to search from the top and find the lead, then insert. It can be inserted if you have a room, otherwise you need to create the children. And children, it's kind of top down, top to bottom approach. Because of that, bottom can be here skewed, bottom can be here skewed. We don't know depending on the data, right? Then idea will be, instead of top to bottom, why don't we create the tree? Bottom to up. And bottom is always the same, right? If you grow up to the top, it's going up, always the same level. Because the bottom will not be changing. Make sense? Then it's balanced. So, for example, so when we create the tree, so starting from here, then if we need a new node, going to here, it's a balance. If we have the data like this, even like this, bottom to up, always balanced. So this is the idea of the B-tree index. So we are going to see the B-tree index this time. Quickly, we have only 10 minutes. Let me use the slide together. So this is what we expect. So I'm going to explain quickly how can we create such a balanced tree. So balanced tree, B tree. To do that, we are going to define the node structure. This node structure is almost the same as the search tree node structure. So just like what we defined here. So suppose that you are going to do the programming. Okay? So we are going to define the node. Node is the block, index block node. So we have, for example, in this case, a P order. So this is the order, the P is equal to 3. So 3 children node pointer. And 3 minus 1 key. 2. This one is the data pointer. This is our node structure. So first, when you start the B tree or B plus tree, define the node structure based on what? The order P. So this is the children pointer, children pointer, children pointer. This one is the data key and data pointer, key and data pointer. So we have such a node class. Then we are going to insert the data 8, 5, 1, 7, 3, 12, 9, 6 in this order. That doesn't mean we are going to insert only 8, 5, something like that. Instead, insert into student table values and the 8 and lead and CS and other information like this. Okay? We are going to insert the entire data, but I'm going to show how to create, how to organize the index. So we need only the key, index key. So same thing when I'm saying the insert the 5. It doesn't mean the only insert the 5. So 5 and the James and the E like this. Okay, but to simplify our problem, I'm going to mention about only the index key. So first, insert A. What if there's no index? We need to instantiate the new node. Okay, so that is the in memory it will be allocated like that. But this is a high-level illustration. Don't be confused. And no child, no child, no child. So this one means no. And solid means pointer. Then, what is the value? 8. And data pointer. This one is a data pointer. 8 will be inserted here. 8, lead, and the CS, and data pointer is number 2. So number 2 will be inserted as a part of index key. Okay? So this is done. No problem. It's the same as the search tree. Then next, 5 is inserted. What happened? We have a room over here. So it doesn't cost to reorder in one block because it's copied into the memory, right? So we can quickly 5 and 8. No children yet. Okay? And the 5 is block number 1, and this one is block number 2, for example, like that. Then, problem is the 1. In case of search tree, how can you insert the 1? Like this way, right? Instead, it's as I said, bottom to up. So, is there any space to insert the 1? This one is called the full of the node structure. So full of block. There's no. What is the blocking factor of this node? It's a 2. Only 2. Then in case of full, what will be the solution? New one. New one to where? Bottom? No. We are going to split. Split the how many? 1, 5, 8. So we have 3 of them and split. First, in case of full, split. And find the middle value. I think that this one will be better. Find the middle value first. Middle value, then based on the middle value, split. So, which means 1, 5, 8. Which one is the middle value? 5. Then, this is important. Left-hand side of the middle value, go to the left-hand side. Right-hand side of the middle value, right-hand side. What about the middle value? It's going up. And 5 will be new node as a parent. This one is called the promotion. The middle value will be promotion. So we can promote the middle value. Not done yet. Then we need to reorder pointer. For example, less than 5, go to here. So this is solid. Bigger than 5, go to here. Like that. So, is it balanced? Yes, it's still balanced. Okay? Because it's growing bottom to up. So always the leaf node, based on the leaf node, going to up. Always the same node. Then we can do the same thing. The key part is in case of full, find the middle value because middle value will be parent. Okay? Then split based on the middle value, based on the parent. Then promote the middle value. Okay. Then what about the next one? 7 is inserted. Same thing. 7 is bigger than 5. Going to here? No. Always find the terminal node, lymph node. So less than 5, bigger than 5, we have a space. So 7, 8. Like that. Why? So bottom to up, starting from the lymph node. So we are not going to use this one, even though we have a space. So 7 is done. What about 3? 3, first find the lymph node. Less than 5. 3, we have a space. 3, no problem. What about the 12? 12 is bigger than 5. This one, no. We are not going to insert it in the middle. Always find lymph node. The 12 is bigger than 5. Supposed to be here, but it's a full. In case of full, first find the middle value. 7, 8, 12. Middle value is this one. And the split. Left hand side, right hand side. Copy, create another one. So 7, 8, 12. So left hand side and right hand side. Based on the middle, 7 and 12. And the middle value will be pattern. Insert here. So 8. Then reorganize all the points. Less than 5, bigger than 5, less than 8 goes to here, no problem. And bigger than 8 goes to here. Okay. So that is done for 12. 9. Find the 8. 9 is bigger than 8, goes to here. So we have space. So 9, 12. What about 6? 6 is bigger than 5, less than 8. So 6 and 7. This is the same as this. Is it balanced? Yes. So, quick question. When you access the 6, so 6 is blah 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 like that. So 6. How many IO? How many blocks do you need? 1, 2, 3. Always plus 1. Data file is here. So what about 5? 2. At least equal or less than the level of this tree. So it's a guarantee. Okay. One last. 0. What happened? Find the location. 0 is less than 5. 0 is supposed to be here, but it's a full. In case of full, find the middle value. 0, 1, 3. Which one is the middle value? 1. And left hand side, right hand side. So we can create another one. So 1, 3, 0, 1, 3. No problem. Then the middle one will be promoted. Promotion means it's an insert the parent. What happened? It's also full. How can we handle full or parent? Same thing. We are going to do the exactly same thing. So 1, 5, 8. 1, 5, 8 for this one. Find the middle value, left hand side, right hand side. So we have two of patterns. This one is 1 and this one is 8. And children node, we will take care later. Data node. Then what about the 5? Promotion. So we have another pattern. 5. Keep in mind, bottom to up, bottom to top, the rowing. So still same level. Last one, less than 5, less than 1, goes to here. Less than 5, bigger than 1, goes to here. This one, should be careful whether this one or this one is bigger than 8, bigger than 5, less than 8. And this. This is the B3 index. Keep going. It's very simple to implement. The algorithm part is this one. Data structure part is only this node structure. Then you can actually do the B3 index. That is one of the reasons the relational database use the B3 and a lot actually now. That we will discuss about later, the next class. But it's easy to implement and performance is really good. So we will see later. Last question. When you search 3, how many IO do you need? 1, 2, 3, 4. What about the 6? 1, 2, 3, 4. What about 8? 1, 2, 3. What about 5? 1, 2. So always equal or less than the level. This is okay. This is better than SearchTree. What about the level is 1000 level you have. Maximum 1001. Minimum 2. Is it really balanced? It's a balance, but we cannot guarantee. Sometimes it's fast, sometimes takes a longer time. So database cannot be late. It's better than SearchTree. It's not really guaranteed time. So query optimizer DBMS need really guaranteed time. That is, this one is called the B3 index. Enhanced B+3 index. This one is really guaranteed time. So next class we will see the B+3 index. The idea algorithm itself is simple. Okay, so we will see the B+3 next class. Any questions? You can keep this one. I will definitely use this handout quiz for your part of final exam. Okay, thank you and.